Okay, so when we last left our heroes, we were looking at different properties of probabilities, and we were getting into the thought of taking multiple probabilities that might share a same sample space, but have been created in subsets in different ways. And so we introduced the idea of conditional probability. And to move through this idea of conditional probability, we had started with looking at mutually exclusive events, and we had done our addition rules. Well, now we're going to add to this the idea of random samples being that they're all equally likely to be selected. And if you remember, if you flip over on your notes page to the previous page, that you can see we have our mutually exclusive events, our conditional probability rule, and on the front part of the page, we had our probability of union, and all of these formulas, again, are formulas that will be used, and they're provided on the note sheet when we work together. So this random sample is just another one of our official definitions. So we've got independent, mutually exclusive. Now we're adding random sample. These are all just vocabulary words that we use. And in most cases, your problem is just going to give all of that as a given. Assume that they're independent, random, mutually exclusive. So it is important when we're collecting our own data, whether or not we can say that something is truly random. We did a poll like the first day of class. You all lied and said none of you in here vape. That's fine. Stigma and all. So then we did a poll talking about like work, who was working in part-time hours or not. Would this have been considered a random sample? Kind of depends on what I'm trying to describe, right? So if I'm talking about this class as a descriptor of the upperclassmen engineering department, I think I might be able to say that this is a random sample, because I've got juniors and seniors in here at different parts of their scholastic endeavors, depending if you're a May grad or a December grad. I could have really like 6 different levels of juniors and seniors in here. And it covers a wide number of engineering disciplines because basically all of the majors include this course as one of the required engineering core classes. And so because of that, for if I'm saying that I'm looking at my population being juniors and seniors classification in the engineering department, I could say this is random. What if I just said USI students? No, it's a skewed sample, right? Because I'm only looking in a singular department. What if I said engineering department? Yeah, it's really hard to get into this class early. We actually have a junior standing label on it as well. So you have to be junior or higher classification to register without an exception. If you've done a whole lot of dual credit and your schedule's weird or you transferred, you might be able to get in. Um, your standing might be different. But yeah, it's assumed that we're kind of skewing it to the upper level anyway. So even for the engineering department, I wouldn't say that this is random. Now, what if I was surveying and I was just standing in the Starbucks at Rice Library and just asking everybody who walked through the door, are you employed? Any level of employment, every person that walks through the door. Well, I'd ask first if they were a student because some of you look young and some of you look old. So I'd ask first if they're a student. So I don't want to have the employees because obviously that skews the sample. They're employed here at USI. But I just ask every student who walks in the door, are you employed? Is that random? Would that be enough? Why? Okay. What if I'm at the loft? What if I'm just asking as people walk through the loft? Is that a more appropriate place if I want a random sample? Skewed towards underclassmen. Yeah, a lot of people that eat that are forced to be on a meal plan, probably not a commuter student either. So we're probably looking resident underclassmen. Where do I go? Where do you think you can actually get a random sample here on campus of students? What do you think? Okay. Okay. Anyplace else? I mean, it's just brainstorming. Anything counts. Okay. So we shied away from academic buildings like the BE. You get typically business and engineering majors. Science Center, you're going to get a lot of Pot College, right? We go over to the liberal arts building. We'll probably get a, actually, no, we'd get the College of Liberal Arts, but don't you have all your like English and comm classes in there? Oh, English is an or. Com, psych, soc, like that should be across because whatever college you're in, health professions, pot, romaine, you should still be taking classes in the liberal arts building. That might be another location, which is right off the quad. So that might be a good spot to get a broad cross section. So when we think about random sampling, to get true randomness, a lot of it comes down to that collection point, right? The positioning, which is the same thing if we're going to try to take things like off a manufacturing line, usually the random sampling is just told, take X number at this interval of time. Every so often grab another one. There's no rhyme or reason. It's just the set sampling plan. Um, a lot of times, if you're looking at doing incoming material inspections, so you're mechanical engineering, you're looking at material properties, again, that random selection is going to be of everything that comes through the door. I'm just going to pick stuff out, some beginning, middle, end, all spread throughout the sample. To try to get that random sampling, right? So it all comes down to contextualizing that. When we make the assumption in our contrived problems that mathematically always come out exactly the way we want to, it's a big jump. It's a big leap. And this is part of the problem with statistical analysis that's done in practice compared to what we do in the textbook, because we get to assume that it's random. But in practice, getting true random data is actually more difficult. It's intentional. It doesn't just happen, right? And so I just wanted to point out, because these baseline assumptions that we're going to say over and over for the next remaining 14 weeks are actually really hard to do in practice. For me to say things are independent, there's actually statistical analysis that I have to do to prove independence. We just haven't gotten to those yet. If I want to show that they're mutually exclusive, I actually have to demonstrate that randomness. I need to demonstrate how the sample was collected. That would be in a methodology that I would actually explain how I ensured randomness. Now, there are times where you don't want random samples. There are times where a target demographic is exactly what you want. And so you can do stratified sampling. You can do practices where you're not doing random, like first piece inspection. You're always going to look at the first piece to make sure that everything's set up correctly, right? So there are different times where you don't want random sampling. That doesn't mean that you can't use statistical tools on it, but some of these things that say assume randomness would no longer be true. And that might change the statistical tool that you use. All right, enough on definitions. So our next little rule, again, it's in the FE handbook, the multiplication rule, shows that when we have the intersection of A and B, we can actually tease that out to say that this is equal to the probability of B given A multiplied by the probability of A. And if you flip your page over here, and you look at the conditional probability law, all we see is the algebraic manipulation of that, right? The conditional probability law and the multiplication rule are the same rule. They're just the various ways of showing it. And depending on which of these you have and which you don't have will determine like how you operate with this. And your homework that we'll do next week together will show that depending on what sort of information you're given in the problem, you're going to set this up either using the multiplication rule or the conditional probability rule. Mathematically equates, but dependent on what variables we're looking to find, the different expressions can be helpful. And you see that this is true for both B given A multiplied by the probability of A, or A given B multiplied by the probability of B. Both of those things are equal to the intersection of A and B, because the probability of A intersect B is equal to the probability of B intersect A. So that transitive property that we established earlier, that's part of why that this is true. So we're going to look, and we have this example, and it says that the probability that the first stage of a CNC machining operation meets the specification is 90%. So 10% of what you're making is garbage. Anybody feel good about that number? Anybody feel good about throwing away 10% of what they do? No, that's not a great number. The probability that it meets specification in stage 2, given that it meets specification in the first stage, is 0.95. So let's think about what this means. Probability it meets stage 1, 90%. At that point forward, only 90% have gone forward, right? Because at 10% there are defects. We've got to rework that, or even worse, scrap it out. Now I'm looking at stage 2. I'm inspecting after stage 2. 95% of them are good. Okay, you're an engineer and you want to say, you're looking, this is actually called rolled throughput yield is what we're doing here. If you're a manufacturing engineering student, we'd be talking about this in terms of rolled throughput yield. And our rolled throughput yield, or the probability that it's meeting both stages, is just equal to the multiplication of those two. And so that is 0.855, or 85.5% of the time you have something that successfully makes it through the manufacturing process the first time. Is this good? But those are high numbers. Those are A's. Those are A's on exams, right? Is that good though? No, that's not good. Rolled throughput yield uses this clause, uses the multiplication rules and conditional probability rules to show us that when you have these dependent interactions, and anytime you have something in sequence, so all of my electrical engineers, everything that you do, anything that you wire up in sequence, whether it's series or parallel, when you're looking at the reliability of that circuit as a whole, can you choose just one part to be faulty? Is it going to work if just one part is faulty? No, because once you've wired that up in series or parallel, they're all dependent on one another, right? Or if I'm looking at mixing concrete or something, and I upset the ratios, and so I reduce the amount of cement compared to my rock and sand and water, right? Is the structural strength going to be the same? It doesn't matter that the cement is good. If I've used the wrong ratio, the overall outcome is poor, right? So every discipline we have things that are happening in sequence. And if one part of the sequence is bad, the overall product is going to get worse. So you as the engineer, this information is just math until we decide what to do about it. What would you do about it? Probability that it's coming out of both stages correctly is only happening 85.5% of the time. What do you do? What would you try to improve? Let's assume that you're capable of making improvements. Where would you go? Where would you look first? Why? Yeah, that's setting up the dependency, right? All of this information about stage 2 is given what we have coming out of stage 1. So fixing stage 2 itself will make a small incremental change, but fixing stage 1 alters that initial condition. It's also the lower of the two numbers. And that's true for any time we're trying to fix a problem, whether it's something in a circuit or something in the manufacturing, we go as far upstream as we possibly can, because every other variable after that is dependent on that initial condition. So we want to work our way as far upstream as we possibly can. And then if we have multiple things happening simultaneously, we go in the order from low to high. But we're always going to move our way back as early in the process as possible to set up those conditions, because everything is being multiplied by that factor after it. Whether I have 2 processes or 20 processes, everything is going to be impacted upstream by those early issues upstream. And so we always want to work our way back. So the math shows us how the formula works. Thinking about what you would do to fix it, that's what you actually get paid for. So we're going to do another problem. And so this is on your worksheet 2-20. And so we're going to work through a few of the different calculations here. Okay, so we have information about product failure, and we're trying to find the probability of failure. So we're trying to find the probability of F. So F is the event that we have a product that fails, and then we have a given level of contamination and the probability of that given level. So if H is the probability, the event that the chip is exposed to high contamination, so we have high and not high. So everything's happening here, high, not high. And then we have the probability of a failure given these specific conditions. So the information that we've been given here is we're given the probability of failure given that it is high. That's this right here. We have a high level of contamination, and the probability of failure at a high level is equal to 0.1. We also have the probability of failure given that it is not high. That's this one right here. Probability that it's not high, level of contamination is not high, so the probability of failure in that condition is equal to 0.005. But it's not enough to say that I could just add these two. Well, probability of failure at high and not high, just add those two together. Well, no, because I need to look, these are those states given these conditions. What's the likelihood of this condition happening? I can't just add these. It's not the same mathematically. I have to actually start by looking at this condition is within a given set, and I have the probability of these H's, the probability of H happening. So the probability of H, probability that it's high, is that 0.2. And the probability that it's not high is 0.8. So now what I've seen is I've got 100% of the conditions, high or not high contamination. I've made it a binary thing. It's either high or it's not high. So 100% of my sample space has now been taken care of by these two probabilities. These are conditional within these set states. So now to tease out the probability of F, I can find the probability of F because I have F given H and the probability of H, and I have F given not H and the probability of H. So now the probability of F on its own is equal to the probability of F given H multiplied by the probability of H plus the probability of F given not H multiplied by the probability of not H. If you think of this given line as a divisor, you can kind of think of it as this, the probability of F over H multiplied by the probability of H over 1. And these cancel out, and it gives you the probability of F. If that helps you to kind of think of it, that we always want, you want to check that when we're doing these, as they get more complicated, that your given should always be then mirrored, because otherwise I'm not finding the right thing. So the probability of a failure is equal to the probability of F given H, or 0.1, multiplied by the probability of H, which is 0.2. That's the first term. So this takes care of the 20% of the time that I have high. And then I have the 0.005 multiplied by 0.8. And this takes care of the 80% of the time that I'm not high. And so this gives us a total of 0.024. And we see that does not equal 0.105, which would be just adding them together, right? So like we do not just add them together. That is not correct because we need to take into account 100% of the states, 100% of the sample space, and that's why we multiply by this additional factor. So we can do this kind of infinitely, as many ways as we want to dissect our sample space. We can draw these little amoebas or lima beans or however you want to picture them. But your textbook loves drawing these little things that to me look like a biology cell textbook type thing. And what it shows is it shows that we have this totality of B, and B contains everything in here. B contains A and not A, and it contains, so we have B is the lima bean, A is the sample space, and the probability of B is looking at the union or the intersection of the two A and B, and then not A and B, those intersections, and then the union between the two will give us the totality. Why? Because the union is going to take out the overlap, right? If we remember the unions remove the intersection of the events. And so by doing the union of the two intersections, I end up with only B because the A and the not A, that's going to get canceled out, right? As I do this mathematically. So the probability of B is equal to the probability of B intersect A plus the probability of B intersect not A. And that intersection can be written as the probability of B given A multiplied by the probability of A, and the probability of B given not A multiplied by the probability of not A. And so I am taking out, if you remember that we kind of like crossed out when we send it up as a multiplication, that like B over A times A, we're taking out all of A and all of not A or A prime. And what remains is simply B lima bean inside B. And so this can be done for as many events as we want to. We could set this up to go further and further and further. So we have an example here, and I'm going to pause the recording and give you guys a second to work this out mathematically yourselves. All right, so the first thing that we need to know is that we need to know that we also have the probability of not B, because our conditional probabilities are A given B, and we have conditional probability of A given not B. And so I have B is equal to 0.8. So not B is equal to 1 minus the probability of B, or 1 minus 0.8, which equals 0.2. When the numbers are small and simple, it's easy to just intuitively write that down. So if you don't go through the full math in your homework or on a quiz or something, and you just write it down, because you can look at 80 and get 20 when you subtract it from 1, like that's not hard math. That's fine. But you do want to include the step. You do want to include the step of finding the complement. So you can just write it down. You don't actually have to write like all of this, but before you start doing this problem, you need to write down that this occurred, and just show the awareness that you actually needed to solve for that. So now we have the probability of A is equal to the probability of A given B multiplied by the probability of B plus the probability of A given not B multiplied by the probability of not B. And now since I have all of this, now I can just plug and chug. So it was the 0.2 times 0.8 plus the 0.3 times the 0.2. And that should have given us 0.22. All right. So the total probability law tells us that when we have mutually exclusive events, that we can just do this multiplication law as far as we want. This whole total probability rule is just the multiplication rule set out for as many events as we possibly want. And so we can keep subdividing all of these. And so again, we see that we have these spaces that have all been noted. B is our lima bean again. So we have the probability of B. To get the probability of B, we just have to be able to segment out everything that's E1, E2, E3, and E4. And how do we do that? Well, we take the place of intersection between B and E1, B and E2, B and E3, and B and E4. And if we know those conditional probabilities and the probabilities of those events, then we can isolate out all of the white space and we can get it down just to our lima bean. So this can happen for any endless amount of divisions that you have. In these examples, it's not going to go above like 3 or 4. But in our homework that we'll do together, you'll see they'll do it out like 3 or 4 times. But it just shows how we have multiple conditional probabilities. And when we take away all of the conditional probabilities, what we're left with is that one lima bean that's occurring across multiple conditions. So last vocab word in this series, in this chapter, we'll be using them again the entire semester. So random, independent, mutually exclusive, all of those are our words. And so how do we know mathematically true? Well, if the probability of A given B is equal to the probability of A, what does that mean? Or below, probability of B given A is equal to the probability of B. What does that mean? For 1 and 2, what are they implying? If I'm saying the probability of A given B equals the probability of A, then does B have any effect on it at all? No. And so if B has any effect, if B doesn't have any effect on it, what do we think of that like overlapping nature? Is there any overlap? Picture the lima bean. Like, do we see any overlap there? If there's no condition, like if they aren't dependent on each other, they're completely separate spaces, right? So this independence we've already kind of talked through in different ways, but the random independent we see following basically the same definitions as our mutually exclusive events that we're having, that if there's no independence, that if there's no dependency there, they're completely separate from each other, then the probability of A given B is the same as the probability of A because they don't impact one another. So independence can just be written out as multiplying all of those intersections against each other because they are all just their own independent events within any given subset. So Bayes' theorem takes this information and says that if we have the probability to find the probability of A given B, if we know the probability of A and the probability of B and the probability of B given A, we can actually invert this. And so this works both directions. Again, we just have these A and Bs as A's coming first, but these are just combining the same laws that we've done before of total probability and the multiplication rule to put it into this condition so that we're actually able to see that if we have both of those probabilities as standalone probabilities and we have that potential condition already looked at, the condition of B given A, then we can find the probability of A given B. And so you can see here that the algebraic manipulation of this would allow you to also find the probability of just A, or the probability of just B, or if we move all of the terms inside out, upside down, and backwards, we can get the probability of B given A, right? So algebraically, I can move any of these terms around on either side of the equation and tease out just one of those variables. And that's the power of Bayes' theorem, is that if I'm missing one of any of these, but I have the others, I can tease it out. And so that's how we use Bayes' theorem. If you want to see it actually derived, your textbook does do that and will derive from the other laws of probability how we get down to Bayes' theorem mathematically. But I don't know that you definitely need that information, but if you want it, it's available to you. So we're looking here, we have the contamination. This was our earlier example. We were looking at the conditional probabilities, and we were looking at the probabilities of a failure because we had the probability of a failure, knowing the probabilities of these levels of high or low contamination, high or not high contamination. And we were able to find the probability of a failure given that particular level. But we can actually find a probability of a high level contamination given that there was a failure. So we can invert this. And so if we know the probability of a failure given high and the probability of a high level of contamination, and we know the probability of a failure, which is what we calculated in the previous example, that's 0.024, then the probability that there is a high level of contamination, given that you found a failure, is 0.83, which makes intuitive sense, right? If you look at all these numbers, it makes sense to yourself that you're saying, okay, I'm starting out with the fact that I'm looking at a failure. So that's 0.024 or 2.4% that I'm going to find a failure. What's the likelihood that it was a highly contaminated sample? Before I even put it into the microscope, I'm betting it's pretty high. Why? Because most of my failures, if you look at this, the probability that there's a failure is 0.1 or 10% is when I have the condition that there's high contaminations. But if there's not high contaminations, it's a very, very low likelihood that I'm going to have a failure. So if I take a failure and I'm asking whether or not this has high contamination, my guess, my intuitive guess is going to be yes, that it is from a highly contaminated sample. And that's what we see here mathematically. What's the probability that it's a high level of contamination given the fact that it's a failure? Well, 83% of the time. So of that point, the 2.4% failure rate, 83% of the time it's coming from a level of high contamination. What does that mean? Well, it means 17% of the time it's coming from low, right? If I'm finding that that's a low contamination sample, which would make me ask, well, what else can cause it to fail, right? It's a lot less likely, but it does happen. So this just shows how you have to find this probability of F first. And so we teased that out first so that we could then invert it and find this other condition. And so in this example, we're going to walk through the entire process. I'm going to switch to graph paper so I have more space. But we're going to look at these three different states. The probability that it receives a good review, if a new design attains a good review, what's the probability that it will be a highly successful product? And if the product does not attain a good review, what's the probability that it will be a highly successful product? So these if statements in B and C, obviously we're looking at conditional probabilities. And so we're looking at these two states of having a good review or not having a good review. And so before we can do that, we need to know what's the probability of good reviews. But what do we actually get the information in terms of? We get the term information in terms of success rates. So we're going to tease out these conditional probabilities to figure out how we get a good review, and then look at those conditions with respect to highly successful products. So G is going to be our good review. Not G will be our not good review because we're going to need that information as well. And we have high, moderate, and poor as our different conditions here. So we're going to start out by teasing out our given statements, and then we will work through this. Okay, so the first thing that we want to see is we have, in the past, 95% of highly successful products received good reviews. So we have a statement that the probability that it received a good review, given that it was a highly successful product, is equal to that 95%. Everybody good with that? How we went from those words to that descriptor? So 95% of highly successful products received good reviews. So this is the condition that it received a good review given the fact that it was a highly successful product. Okay, 60% of moderately successful products received good reviews. So again, the probability that it got a good review given that it received a moderate review. That was equal to 60%. Then we have the probability here, 10% of poor products received good reviews. So the probability that it got a good review, given that it was a poor product, is 10%. Now, obviously, with these being conditional probabilities, this does not add up to 1, right? Because these are all given conditions. It's probabilities within a specific condition. So we also then are given, well, what's the likelihood of success? So we have the probability of products being successful is equal to 0.4, or 40% of their products are successful. The probability of it being moderately successful is 0.35. And the probability of it not being successful, poor performing product, is 0.25. So question A is asking, what's the probability a product gets a good review? Or the probability of G. So the probability of G, I have all of these probabilities of G given a situation, and then I have the probability of that situation occurring. So I can just add all of these up. The probability of getting a good review is equal to the probability of a good review given that it's a high performer, multiplied by the probability it's a high performer, plus the probability that it gets a good review given it's a moderate performer, multiplied by the probability it's a moderate performer, plus the probability that it gets a good review given that it's a low performer, multiplied by the probability that it's a low performer. And so the numbers that go into this are 0.95 times 0.4 plus 0.60 times 0.35 plus 0.10 times 0.25. So I now know the probability of good review independently of how high performing they are. That G was the lima bean. If I had drawn this out, I have this sample space. G was my lima bean. And a large amount of them, this is not to scale, had that high performance, moderate, and poor. So I had my high performance, my moderate performance, my poor performance, and these are all the good reviews I'm getting. And again, not to scale, because the majority of the time that I'm getting my good reviews in high performance, my good reviews in moderate performance, my good reviews in poor performance. And so by doing this math, I'm able to see the likelihood of that happening. All right. So the next question is, if I have G, if I have a good review, what's the probability that it is H? So I'm looking for the probability of H occurring given that it's a good review. So this is equal to the probability of the inverse, right? That it's good review given that it's a high performer, multiplied by the fact that it's a high performer, divided by the probability of getting a good review. And because I already solved for the good review, I can substitute the math into this. So it's 0.95 times 0.4. Then I divide that by 615. And that's 0.618. Part C asks, if it's not a good review, what's the likelihood that was highly successful? Now, what people want to do here is they want to just subtract 1 minus 0.95 because they say, well, you know, the probability that got a good review, given that it's a high performer, is 0.95. So if I'm saying it's not a good review and it's a high performer, right, it's just 1 minus 0.95. Or people want to do 1 minus here. If I got a high performer and it's a good review, then, you know, that it didn't get a good review, just 1 minus that. Like people try to do the complement of these other conditional probabilities, but the whole premise is wrong because the whole premise of these are starting with G. And in this case, we're saying it's not G. So what I'm actually looking at is not these conditional statements complements. I've got to start with the complement from there because I'm saying if the product doesn't have a good review. So the first thing I need is the probability of not G. So I can't just take a complement of this one or this one because my entire premise is that it's not G. And so not G is 1 minus the probability of G, which is equal to 0.385. So that's the first thing I have to calculate is I have to make sure that I'm looking at the correct complement because what I'm asking for is the probability of a high performance with the condition that it did not receive a good review. Probability of a high performance given the fact that it didn't have a good review. So I can use the same formula here, but now I'm using this idea of not G. So now I can actually take the inverse here. So I have the probability of G given H is equal to 0.95. I can take the complement of this because not G given H is equal to 0.05. And what have I found? At this point, this is all dependent on this idea that it has a high review. Because within the fact that it's given that it has a high review, I have these high performing. This is all given the fact that it's high performing. So within the idea of just that it's high performing, I can find good or not good, given that it's high performing. What I'm doing is I'm only looking at this space. I'm only looking at the space of it being high performing. I'm not looking at any other good reviews. I'm only looking within this sample space of it being high performing. So given the fact that it's high performing, so only looking at this wedge, I can do good review, not good review, and that's the totality of this. Good review, not good review, given that it's high performing. I'm only looking at that part of the wedge, right? So this calculates the lima bean. This is looking at what's the probability that I have a high performance given that I'm in a good review. Well, that's this portion of the lima bean. This is in this high review portion and that I have a good review. So here's my good review space. And this is the part that overlaps with the high performing. So I can find the probability that it's not a good review given that it's high performing. And I'm looking at this sample space. So that's why I can take the complement of that. Then I have the probability that it's high performing as that 40% already. And I calculated the probability that it's not a good review based on my initial calculation that it's good review. So my good review, that's why I keep saying this isn't to scale. My good review should take up 60% of this rectangle, and well, 61.5% of the rectangle should be taken up by the lima bean. And then the remaining portion is that 38.5% is not the lima bean. And so now I have everything I need to figure this out. So the probability that is a high performer given that it didn't get a good review. So this means critics are dumb. That's what I'm asking. How often are critics dumb? That I can look at the probability that it didn't get a good review, given that it's high performing, multiplied by the probability that it's high performing, divided by the probability that it didn't get a good review. And so the didn't get a good review, given that it's high performing, is that 0.5. Thank you that we derived. The probability is high performing. That was given to us. And the probability that it didn't get a good review is the complement law that we used above. And so all of this comes out to 0.052. Roughly 5% of the time. Even when they're not to scale, drawing these can be helpful, like on an exam, drawing the space to figure out what thing you're actually looking at, of what spaces are overlapping. That can be really helpful on an exam. Since we're going to do the homework together on Thursday, week from today, we'll have additional problems like this. And I'll probably, so if you want to test yourself, you could do the homework in advance and come with it done and just use it as a review with me doing all the solutions so you can make sure that you're right. That would be like, let's call that the good student method. That go ahead and do the homework and use the in-class time to check yourself to make sure, and then you can ask any questions, places where you deviated to say like, would it still work if I did it this way? Because that's one of the things that I see with conditional probabilities is people will be like, oh, but why doesn't it work to do this? And it's that idea of what is the inverse of something? What is the complement of something? And a lot of times it can help to draw it out. So we can do that on Thursday. If you look at it and you have no idea where to start, come Thursday prepared to ask questions of just like, how do you even set this up? Because that's the other thing I see on exams is people take something like this and they can't translate it into that. That's the other thing that gets people on exams. Once you have this, setting up your equations, I mean, you're multiplying. The math is easy, right? But getting from a word problem to this and understanding what things can be complements and what can't, those are the places that people most often see confusion. So we'll walk through those slowly on Thursday, but I recommend that you take a stab at it or at least read through it so that you have an idea like, how would I start this if I was doing the problem? That will probably give you the most bang for your buck on Thursday. All right. Enjoy the, I guess it's just a day off from lectures, and enjoy your weekend if I don't see you before.